Hello, good afternoon. Welcome to the stream. We're going to do some more Essentials of Compilation today, as we always do. We had left last time. We were in the middle of doing some tests for select instructions. Kind of backtracking because we hadn't really tested some of the things that were done in that pass. I don't know, Willie Renatius, if you are on the stream yet, but you two have convinced me to use Birdie. So we have a little bit. Hello, Birdie and Jordan. Yes. We have a little bit of review to do. I did a little bit after the stream last time to try it out, and kind of like the output. So I think the challenge in this particular case is twofold. Because the capabilities of our language are becoming more complex, it kind of makes more sense to use snapshots, because otherwise I have to rely on the particular layout of a thing in the abstract format to be consistent when I make changes. So that is brittle in a sense. So snapshots help with that in the sense that instead of having to adjust a bunch of assertions, we can look at what changed in the diff, right? That's a benefit. On the other hand, it's on me as the programmer to verify that the snapshot still makes sense. So I think it's still going to be useful for us to list all of the assumptions that we have about that output, and then manually verify that they are correct. So we are adopting snapshots. Welcome to the stream, Willie. Welcome to the stream, Renatius. And we're going to get started. So let's do it. Okay, so last time we were trying to make this test, and here in, I don't know if you can read that very well because it's very low contrast, but here in the comments I put, what are the things we want to verify. So we go through them real quick. This is our program. This is the body of the program. These are the two functions it defines. Inc, of course, is add 1 to the integer argument. And map is apply this function that is integer to integer over a vector that contains two integers. So on each field of that vector. And it does sort of what you would expect. So what do we expect out of this? Based on the semantics of our program with functions that you can call, define yourself and call, we know that function references are going to be put into registers to be jumped to or called, right? So that we'll do indirect calls. This means we need to use this LEAQ instruction. So basically load the effective address of map or inc into variables. So we expect main to have those instructions in it, in any order, honestly. Then when they are called, we expect them to move variables or values that we care about into the argument registers. So RDI, RSI, etc. The order of the argument registers is important, but we expect that to be happen. So map receives two arguments, one of which should be inc that was loaded into a variable, right? And the other one being this vector that we construct. This in particular is kind of a complicated assertion to make if we were to do it with writing manually, like handwritten assertions. That would be hard. And then, inside map, we call the past function twice, and they each receive one argument. So this is like, in map, we're loading whatever the result of vector ref is into RDI and passing it F, and then vector ref again into RDI and passing it F. So, and then on the return from those calls, we should capture return values into the REX register, right? So main copies the result of calling map into a variable, and map copies the result of calling F twice into separate variables. So that's what we expect to see. So I did this, and I've already accepted the snapshot, but we're going to look at it. So let's split this right. Oops. Split this right, so we can see our assertions, and then let's look at the snapshot. Okay, so here's the inc function. And what does inc do? So inside the calls, we're moving things out of the registers into a local variable. That's the x3 that was defined in the x is the argument. This has been unified, and then so it's moved into x3. Move x3 into REX so that we can operate on it, and then add 1 to REX. Okay. I lost the beginning. How do you find Birdie? I've used Birdie before. I like Birdie. It's good stuff. Okay, and then it's going to be jump to the conclusion, which is going to take care of all of the other stuff. Okay, so we verified that inc does the argument moving, which is good. So moving to and from. All right, so we can call inc basically done. Let's skip over main and look at map. Okay, so map is going to take 2 arguments. So it's going to move out of RDI and RSI into the variables that are defined, F and V. And then it's going to move V, because V is a vector, right? It's going to move it into R11. And then it's going to index into that vector. So this is the vector ref instruction. It derefs that into temp1. Okay? And then it's going to move temp1 into RDI. So that becomes the argument, and then it calls F. Okay, looking good so far. And then it's going to move RAX into this temporary variable that is going to be the first field in the returned vector, right? Okay. And then we're going to move V2 back into R11. Although honestly, this may be a redundant move because R11 is not. I think it's a free register. It's not in the callee or caller saved. So it would not conflict with the ABI, but this is just basically repeating the same pattern of we need to do vector ref. So we need to move this variable that we have into R11, deref off of R11 16 bits. No, that's not 16 bits. That's that's 2 words. This is 1 word. Okay, and then you can move that into temp2. You'll note here that like these temp things, these are a result of the remove complex operands operation. It's part of that pass. Okay, and then we're going to move temp2. So we've done this vector ref. We're going to move temp2 into RDI again, call F, move REX into vecinit2. Okay, so now we've got those 2 results of calling F, and then we're going to do the dance of allocating the vector. So, get the free pointer, needlessly move it around, add 24 to it, compare it to the end of the free space, And then, you know, jump if it's less than to block 2. Otherwise, jump to block 3. So jump block 3 should be the call to garbage collect. Block 2 should be the construct the vector bit. No, block 2 should just be jump, just pass through. Okay, so we're going to skip over block 1 right now. Block 2, yeah, so this is just void. That's part. Yeah, we don't underscore 6. Who cares? Void. And then it jumps to map block 1. So this is the success path. Map block 3 moves R15, which is the heat pointer, into RDI, and 24 into RSI, and says call collect. Okay, and then jumps to block 1, which we already saw does. Okay, so this is going to be move the free pointer into R11, add to it. So this is like, hey, yeah, we have the space, right? Okay, and then it's going to, so this is the vector tag. 4 is the magic number on that tag byte, and then, you know, we'll move that into the 0 slot on that vector, and then we will yeah, so we move R11 into this allocated vector. So this is the allocated and initialized vector, and then it's moving it back because reasons that will get eliminated later. Okay, so now we have the result of calling F moved into the spot off of R11 indexed with 1 word. So it's, you know, off to the offset from the initial part of the vector. There's a void bit in there because of previous phases. Okay, and then we're making sure that, you know, the allocated thing is still in R11. Not strictly necessary, but probably what will happen is, like, this will get allocated, the register will be allocated to R11, and then this will be a redundant move, and so it'll get eliminated. Okay, and then the value we captured from calling F the second time gets put into R11 offset 16. Okay, so we filled into the new vector, and then, you know, there's another void bit, and then we're going to move the vector into RAX, and interestingly, like this R11, it might become RAX, we'll see, and then jump to the conclusion. So map makes sense. This is a lot, mostly because of all of the vector business, so I think that we're okay there. Let's look at main now. So just to check, you know, map, we saw it pull 2 arguments out. It called the past F twice, each with 1 argument, and then it copied out of REX into local variables. Okay, so we've covered the requirements for map. So let's look at main finally. Okay, main. Here's our LEAQ. So we've got map, we've got inc, we put them in temporary variables. Cool. Okay, and then we're putting 0 into the initialization of this vector. We're putting 41 into the initialization of this vector. And then we're doing the dance of checking, do we have enough space to allocate this? So we jump to main block 2 or main block 3. We're not going to find anything interesting in those. This is basically the same as what we saw in map. How long until you can run the programs? Well, I don't have an x86. I mean, I can write, and that may be a good project for when we're done with this chapter, is do an interpreter of x86. That would actually be useful. The student materials, IU compiler course, they do have a, let's see, the Racket support code. So there is an interpreter for x86 in here. I believe there is. Shoot. Well, if there isn't, then we should just write one because, you know, even though modern processors are weird, um, we could emulate them pretty straightforwardly, I think. Yeah, let's look in here and make sure it's not in here. No, this is just the book. Okay. Let's look at the Python support code, see if there's any. I would expect to see an interpret. Okay, racket interpret x86.py, right? So you know, this is not going to be too bad. There's things in here that I didn't expect. Is this generating a racket program that interprets x86? Is that what it's doing? Yeah, it's like it's calling out to racket. Okay. Maybe let's look back at the racket support code. There's probably an interpreter in here somewhere. Just is it interp? Okay, so they have x86, and I think these are for each chapter. So we should look at these. Gradual to me says this is the gradual typing chapter. But let's look at maybe interp sudo x86. Nah, it doesn't have a symbol outline. Okay, so this provide is saying what it's exporting. If I can spell sudo, I might be able to find them. Okay, so let's look at interp x86. It looks like we've got a partially applied function there. Let's say define public. Okay. So yeah, I think that might be a good place to do this. Another possibility is that, and a pretty straightforward one, I think, is we could set up a Docker container, and use macOS Rosetta to emulate x86, and then just run our assemble our program and run it in the Docker container. The thing is, though, we don't have I/O. So we would only be able to tell the output of the program, because the program has to return an integer, right? By the return, by the exit code of the program right now. So I feel like an interpreter might be more useful. Anyway, nice little tangent. Thank you. Okay, so checking in on main. So main block 2 and main block 3 are basically just the branches for garbage collection. We've already looked at that. So let's look at main block 1. Okay, so allocate the vector, put it in this variable. Okay, so then move the 0 into the first element of the vector, move the 41 into the second element of the vector, and then pull the vector out into this temporary variable. And now temp2, we want to make sure, look at the data flow here. Temp2 is ink, so that's the pointer to ink. Okay, so we're moving inc into RDI, which is first argument register. That's good. Moving temp6, which we just allocated this vector, moving it into RSI, argument 2. And then we do indirect call queue of temp1, which we determined earlier is map. So there's our call to that. Then we move, so this is, I'm just trying to go through all of the assumptions that we want to verify. Okay, so then we're moving the return value of that REX into a temporary variable. And then we're using R11 again as the vector register to deref into it. And that gives us field 1 out of that vector and into REX. And then we are returning on our program. So again, returning 42, like everything. Okay, so good and bad. This would be way harder to do with manual assertions. On the other hand, I had to read all of that and make sense of it. Now, it took longer because I was explaining it to you, to be fair. But I feel pretty confident about this. So we are going to put a pin in here. We're going to, I'll just use the UI here. Okay, so I don't think that there were any other tests that we needed to do that we didn't already have manual assertions on. So I feel okay with that. Birdie. Okay. Okay, so now we can go back to the important stuff that we were working on, which was allocation of registers. So really quickly, I'm going to look back to the history. So we did, so we added this arity to the indirect call queue. We moved things off of the program into the definitions. So the program is just a list of definitions. And I think that, okay, so we handled build interference. So that was part of liveness analysis. Oh, those liveness analysis should be uncovered live, right? Build interference graph we handled. I think that we need to look at the tests for that. Let me see if we updated the tests for that. So we did some stuff with select instructions because of that. Okay, uncover live was rewritten. Okay, so we did uncover live test is still commented out. So we need to go back in there and figure out what needs to be fixed. So I think that's our next step. And there's no build interference test that we modified, I don't think. Let's look at the build interference test. It's all commented out. So I think that we need to handle this. And this is all about asserting that we're creating the right conflicts based on what we understand about liveness. So build interference comes after uncover live, if I recall correctly. Let's go down here. Yeah, so uncover live and then build interference. So let's go and fix the uncover live test, which is going to be uber fun. Okay, so yeah, so let's fix this. I'm kind of making that mechanical change everywhere as we go. But let's go back up to the top. Okay, the other thing that we need to make sure, so this is like manually looking at the a block, a single block. Maybe what we need to do here is go to figure 35. Imagine that's 3.5. Okay, so here's 3.5. Yeah, this is what we were looking at. I don't know that this is necessary to redo completely, but I think that what we need here is okay, so new block. Let me look at that. Yeah, it just returns an empty block. Okay. So what we need here is right, this is the set of expected live after. Right. Okay. And you know, this pass takes a program and returns a program. So it's just modifying the things that are inside that. So I think we do, we'll say main, new definition, and I think that we need to do, we don't need the base program anymore because it's just the definitions. So we'll say this is main, and we're going to put this. And what do we do for the new definition? Okay, so we need, it's label, not name. Label. Return is dot integer t. Okay, so this is not body, but blocks. Okay, so now so I think that what we say is this is going to be this is going to be main, but we're going to replace blocks with the expectation here. So we could also do snapshots on this. Shoot. Okay. I need to check everything here. Okay, so let's close it. Close that. Close that. Close that. Okay, close the block. Close the tuple. Close the list. Close the dict from list. Close definition. Close list of definitions. Okay, so we still have a problem here. Something's not syntactically correct. Let's comment out these other tests. We'll do them one by one, and I think that'll make things a little easier. It's still not working. Okay, so there's something fine here, but the formatter's not working. Gleam format. Okay. I don't know what was happening there. Okay, so that test still passes. Let's run the Gleam test again. Okay, so, and I need to make sure that we remove those echoes from select instructions, because those do not need to be in there. Yes, I think I removed this, and then I abandoned that change. Echo. Okay, so that's only in that one place. Good. Okay. So that was good. That was fairly mechanical. Let's go ahead and fix the next test. And I think it's going to be basically the same. We'll do this. So this is going to be, get rid of this. This is going to be main. Except we already said that. Okay, P2 is going to be, we're just modifying main here. And let me, because this is the same thing, let me do this. If this gets to be too similar, we could do a function that does this comparison, like, hey, give me a block, I'll turn it into a program and run uncover live, and then, yeah, do the assertion. That could be bad though, because then, like, if it fails, well, which test did it fail in? It failed in this other function, right? That would be bad. Okay. Maybe what it could do is just, you know, given your main block thing, you know, take the live before and live after and stick them in there. Yeah, I mean that's a possibility. It could just construct the second program for us. Okay, you know, I'm not expecting these, when we do this transformation, I'm not expecting these to cause any issues, because we fundamentally haven't changed the algorithm. But we will need to check the things that changed about this for this chapter. Okay, so this is multiple blocks. Okay, let's do let main is x86.definition, and we're going to do this thing above like this, except this has multiple blocks, so we can just do that and then say this is x86.definition main with blocks is this dictionary. Okay, so now, since we have multiple definitions, we need to deal with formatter's not running again. Do I have a syntax error here? I don't think so. Yeah, it's just complaining about this. So let's do, we're going to do let assert x86.x86 program. And we're going to say p2. Let's rename that to main2. And here it's going to be main2.blocks. What's wrong here? Oh, capital. Okay, and then here we'll do main2.blocks. And again, here's another thing. Okay, now it's formatted. Here's another thing where we could potentially use snapshots. I think that the assertions I want to make here are pretty important about the order of, yeah, we don't use that. The order of liveness analysis. So I think that that's important. All right, we're gonna do the same bit again. Okay, we're gonna make this be x86. Come on. This is going to be a let assert because we're matching. Okay. Right, okay. So we got these assertions correct. We are going to do like we did above. So we don't need the base program. This is just going to be I think I need to look at the logs and see why this is not, why the formatter is not running. Let me see. So I'm looking at the menus here. Is it Command Shift I? Yep. Okay. Okay, so we should be able to see if that one passed. Yep. Good deal. All right. And we're on to the last test that needed to be re-enabled. This one actually uses the... Okay, this one uses this, and I actually think that there might be some bits here where we want to use a snapshot. Because it's a more, look at all this. This is a more complicated. Well, let's uncomment it, and then we'll fix it, and then we'll see what we can do. Okay, so the order of passes is incorrect here. We need to fix that. So let's just copy that from select instructions test. And then we'll update it. Okay. All right. So here, again, we need to do this let assert because we want to match out that this just made one. And let's rename that to main, and body is going to be blocks. Okay, and this is a dump of the program from previous, and I don't know that it's useful. We have an old version of the graph here. It might be useful to do a birdie snapshot from that, but I'm just going to delete that. That's no longer useful. Let's run the test. Okay, where did I make a mistake? This record update specifies all fields. Okay, so we have a little bug there. Not a serious one, but let's convert to pipe. Convert to pipe. I like those to be on separate lines. Okay. Okay, so we had a failure. So let's look at that. Line 78. Wait, line 78 of here. So we have a bug in our algorithm somewhere. Where did it occur? It's being caused in probably this test. Because I bet if I comment it out, it passes. Yeah, so it is this test. Here, let's just undo. Okay. Let's look at so we're going to go back here. So uncover live comes directly after select instructions, which does mean that we need to have constructed the basics correctly. So what are we doing here? Here we have a loop of trying to analyze our data flow. We have our context flow graph, or control flow graph, excuse me. The blocks that are in this function, and mapping Okay, so conclusion is just setting up the baseline live after. So the mapping must be the live after sets. And they're lists, so they're associated with instructions. Okay. So here, if we are working on a particular node, we get its inbound neighbors. So what's jumping into it? It's interesting this works on the other ones and not the while. Okay. So it's this line that fails. So we're folding over the set of neighbors. And we're getting the live before set of each of the neighbors. So somehow there is an edge here that results in an empty, or like a non-existent mapping. Okay, so what I'm going to do is I'm going to start with this and say echo the result of creating this initial mapping. This is going to get really noisy, but here we go. Okay, so these are from the other ones because we manually named the blocks. Here's the one from the parsed program. So conclusion. Oh, you know what happened? The analyze data flow, it just blindly inserts conclusion, but we've already prefixed the conclusion with the name of the function. So this is the problem. It's looking up main conclusion and it doesn't find it. So, okay. So for the definitions, and here we need input.label. So that's going to be the prefix, right? Analyze data flow, and this is going to be prefix, give me a string, and here we'll do prefix underscore conclusion, and that should fix that particular bug. Not quite. Now we've broken a lot of things. We still have this problem here. But now in all the other ones, I need to make sure that they jump to main conclusion in the test. So all the manually created blocks. Okay, so we're going to find conclusion. And we're going to replace it with main conclusion. Okay, so let's see if we were able to restore those tests. No, they all still fail. Okay, so we have work to do. All right, so we were looking for an uncover live line 30. Okay, so analyze data flow, returns a dictionary from strings to lista. Okay. Map values. Okay. So somehow we're getting oh, is there? Yeah. So here's the mistake. So I need to do remove. Yeah. Let's pull that out into variable. That could be potentially problematic to have to update twice or more. That was the problem, is that there's a block there that doesn't exist in the original source because we haven't added it yet. Okay. So we're still failing on, these are passing. We're still failing on the while loop test. Okay, so now it's just about naming in our test. This is like expecting block 1. This is main block 1. This is not start, this is main, although I'm regretting that choice because I think that what's going to happen is the prelude is going to be named the function, and we need to go back and fix that where we generated it. All right, now let's fix those. Okay, so I'm going to remove this echo now that we know that we're creating the mapping correctly, and we should have no output. Okay. So now we have uncover live for loops. We need to do this, and this may be where I do snapshots. I'm a little bit concerned about that becoming complicated, but let's forge forward. So let's use one of the examples from this chapter or one of the examples we did before. I will start with the simpler one, which is just this. Yeah. Okay, and then for here, I'm going to pull this out into a separate function. Here. Convert to, no, extract function. Okay, and then we're going to rename it. That's kind of weird. Okay. Pre-passes. Great. What? Editor went psychotic on me there. Okay, so now we'll do we're going to do something similar to what we did in the select instructions test with this snapshot. So let's do uncover live. And here, the interesting thing is, here I simplified the snapshot to just be, each function and its blocks. But what we care about here, and let's put this back in here. Okay, so we're gonna pull out the definitions again, because the program is just a wrapper around that list of definitions. So let's do a list map. Seriously, we don't have a Gleam list in here? Okay. All right, we're going to do the same thing. I think that what I care about is the contents of those live after and live before sets, which is the whole point of this. We could do for each block, look at those specifically. Let's run this test and see what we get. What's wrong there? Why is that not imported? Okay. Okay, so let's look at the snapshot. All right. And we're gonna pull this off to the right so we can see it. So here's our program. Where'd it go? I need to move this down to the bottom. Okay. So expect inc to have, what do we expect in its live before? Like, so we will be expecting the argument registers to be live before. REX live after, because we're moving the result into that. And here the live before this would be the argument registers, because we wrote to them. And the live after REX. So yeah, let's look at this and see if it makes sense. Okay, so this inc block is what we've seen before. Move from RDI into X1, X1 into REX, add 1 to REX, and then jump to the conclusion. Okay, so what is the contents of this block? Let's look at that real quick, because I want to make sure that we're correct. So the block, this is the live before set. So right, RDI, which is the argument register, and RSP, which is stack register. We always have RSP live. Okay, the live after set. So in this one, And this, remember, is always computed from the bottom up, from the end toward the beginning. But we expect RSP to still be live, and now this x1 variable is live. RDI is no longer live because we moved out of it. We read from it, and we wrote to x1. And then we write, so that in the next one, we move from x1 to write to RAX. So RAX is live, x1 is no longer live. And then, yeah, through the end of it. That's what we expect in Inc. Okay, that looks good. Okay, so main, we're loading Inc into temp1. We move 41 into the argument register, and then we tail call to temp1. Okay? So, there is no live before set. That's interesting. I would expect RSP to be in there. But we also do a tail jump, so maybe this tail jump does not preserve RSP. Because it does not read from it. Okay. Right. Okay, so then we expect temp1 to be live after that instruction. RDI got a value, and temp1 are live. And then, this tail jump, nothing is live after that. That's interesting. I think I want to be a little bit concerned that this is empty. But maybe it doesn't matter. And because we're doing a tail jump, there's no need to capture REX, so we don't need to consider it live at this point. Inc is writing to REX, right? You can see that here in its last live after set is REX. I really dislike this particular representation. I know that it's like a compatibility thing, but why not just set from list? Anyway. Okay. I know the internals are, hey, a set is actually just a dictionary with, empty list as the value for each, but okay. There's actually a set implementation on Erlang that doesn't use maps. I think it's its own data structure, and it's not ORD sets. I'm not talking about that, which is just a wrapper over lists. Okay, so I'm okay with this snapshot. So let's go ahead and accept that. And then we can run Gleam test again. I think I'm okay with that. I am a little bit concerned about this, the main not having RSP live at the end, and I'm wondering how that occurred. Let's see if we can figure it out from the code. So if we go into analyze data flow, oh right, so nothing jumps to main conclusion. That's really interesting. So main, because of the tail jump, it doesn't jump to main conclusion, so it's not connected to that with an edge, and so it's keeps an empty live after set. I think that's okay. Does bug me a little bit. Does it bug you? Like this assumption that our program will always jump to its conclusion. Doesn't doesn't fit anymore. It also, I think, raises an interesting issue, specifically for tail calls. And maybe we can see if this is in the book. But specifically for tail calls, do we need to be able to do the data flow across functions? I don't know the answer to that. Now, obviously, if this if this were tail calling itself, then we would have a block named, tail jump main, right? In which it would get a live after set from having that edge between those two blocks. But or if like ink did something internally where it tail called itself, we could have, hey, I'm going to tail jump to ink, and then we have the data flow filling in correctly there. But in this case, we don't. Let's have a look at what the book says here. Okay, so we already handled the issue of, tail jump and indirect call queue, saying read and write locations, Target field of tail jump and indirect should be included in the set of read locations. We already handled that. So that's interesting. Okay, we're gonna have to, this paragraph like baffled me last time. We're gonna have to reread that. So let's look at build interference. We have updated this, and I think that what we did was right. So here we did the vector thing. I think that we're okay here. So let's see if we can re-enable this test, and let me copy that pre-passes thing, and we're going to update it for this test. This will be uncover live, and we need to go to the top. So this is x86 base, this is x86 def call queue. All right. Here we go again. Okay. So let us mechanically. Oh, well, that's dumb. Why did it do that? I must say mechanically. If it were actually mechanically, I'd have the computer do it for me. But we're gonna do a lot of this business again. So let's see what we need to do here. Okay, so we don't need this base block, or maybe we do. So our main, okay, so the body is going to be instructions. Okay. And we need to do, this is L tube, we need L fun. Okay. So now we don't do this. delete it. Okay, so now we're going to say let assert 86 program p2 and okay, so that wasn't too bad. We'll do a similar thing here, and let's rename this main2 just so we're clear. All right, let me get and I think we should probably do that to be clear. That would be correct. All right, down here. Okay. All right, I'm going to copy all this business again. Except that we're going to have there's a problem here in that we need to call uncover live. Oh no, wait, this already set the live after. Okay, so this one actually hold on. I want to see what the diff is. What did we do before? Shoot. This did not set the live before. We did not call uncover live in this case. Okay. So that's fine. For this one. For this one, I think we need to retain no, it set the live after as well. Okay. So we need to put that in here. Okay. Yeah, and this one we are calling uncover live. So let's go up here. And we're going to copy this, but we'll omit the live after bits. And then this goes up in here. Okay. All right, now we can do our let assert business again. And save that here. Format, please. Okay. Let's rename this main2. Okay. And that was a bit more complicated, but the main thing there is that RSP and A are live at the same time. Okay. Let us continue. Looks like this one is going to have a similar thing. Right, so let assert x86.x86 program p2, and let's rename that to main2. Okay. Right, fine. Okay. All right. So we've got, yeah, I need to fix this parsed function. We're going to import these other passes that we don't have. Let's copy this parsed function again. It would be potentially nice to put this in a this is parse.tokens, parse.parse. Okay. This would be nice to kind of put it in a utility module, but could be problematic. Let's see if we broke anything with our test. Okay, we did. Oof, that graph. Okay, so here we are with this problem again. So we need to make sure that our manually constructed sets of instructions never jump to plain conclusion, but jump to main conclusion. Oops. So we're looking for conclusion, and we're going to replace with main conclusion. Okay, that should fix that. Fixed several of the errors. So now we have an issue with vector. Okay, this is line 253. So we expect a conflict between Alex6, which is the vector, and RBP. And the problem is in IG has conflict. All right, let's go look at this function. Okay, so this is graph has edge. So it just returns a bool. So there's a question here. All right, so this is saying get me this node, its outgoing set. So does it have an outgoing edge from this node? And if there is no node, or if there is no set of outgoing edges for that node, return the empty set. And then does it contain this, right? Okay, so from x86 location A to x86 location B, the question is, and it's going to be hard to see here, let's just go here. It's interesting it happens here, but not, or it doesn't happen on this one, but it happens on this one. So I think We're going to comment out these other assertions for now. Let me put a line here because I want to see. Let's see what happens if we just check that one. Okay, that's fine. What happens? Okay, so this is the one that fails. Right. So what I want to do is go. What's wrong there? Why didn't it import it? Fine. I don't think that that's actually what I want to do. Let's not echo it. Let's do io.println, because pretty print turns it into a string. So pretty print format. Thank you. Boo. Okay. So we're going to print that out before. All right, so this should be a little bit easier to read up here. Before the assertion. What are we looking for? We're looking for part of the problem is this graph format. The interference graph, we need to look at its definition again. Okay, it's just a graph, x86 location, and each node has those things. So, and our custom graph here, so it has the nodes, it has the incoming, the outgoing. So we need to make sure that RBP is in the nodes. Maybe we can do a quick check here. So maybe we can say assert okay graph.getNode for this. Say let assert okay. Here, import that. Did we already? Okay. And this will be main.conflicts. So let's start with that. I want to look at this more closely, but let's scan it real quick. Like, we should have all the registers. They should exist in there. So yeah, so here's RBP. And that's its, you know, assignment. And then that's its saturation set. Let's keep going. Okay, so that's the nodes. So I think that we can either look for so we look in the incoming or the outgoing. Like, this is a, I think with The interference graph is a undirected, right? So add conflict, yes. So it inserts undirected edges. So it should be both incoming and outgoing. So you could flip those two and say they're in conflict, and it should still be correct. So this assertion that's failing here. Oops. Let's really quickly run that test. Yeah, okay. So we know that RBP is in there. That's not. We could do. We can see what's in the conflicts there for that node. Okay, so it has R11, RSP underscore 7, and vecinit 5. Okay, so we potentially have a problem here with the live sets, which would cause this to not be in conflict. Because RBP should be in conflict. It's the base pointer, right? So we have a problem there. Where did our bug come in? Let's look at this particular program. So this is leaving that out. We'll notice that RBX is not in conflict. These other registers are not in conflict. And I wonder, no, we have some commented out assertions that were from a long time ago. It's interesting to me that R11 is in conflict. Right, so this assertion, tuple type variables must conflict with callee and caller save registers. So we have a problem in build interference that it's not adding those. And I would expect this to add them, right? Okay, let's see what happens when we run this. We are never hitting that. But this is only triggering if there is an indirect call queue or a call queue. So maybe this assumption is incorrect here because we're never doing a call. Right? maybe this test just makes the wrong assumption here. We need to construct one that I think will be better at triggering this condition. So let's maybe, the other thing here that bugs me about this is this makes assumptions about the algorithm that assigns variable names, right? So let's make a program that does this a little bit better. So I think here, yeah, these assumptions are okay if we have a call in the body of our program, which we don't. These are primitive operations that get expanded by the compiler. So I think let's just make a new one. Okay. So let's do something similar to this. And then we'll make some assertions about the conflicts. Okay. So let's construct the vector like so. Okay. And then let's have another let. So this is live across a call. Okay, so I'm going to get rid of this. The read is just a call, but this should make it have conflicts with those registers. So let's have a look at before we make assertions. We want in neighbors for main.conflicts, and we can do this for the callee and caller save registers. So let's just pick some. Like let's just pick RVP. I think that's probably the easiest way to do this, because this was the one that was causing this one a problem. Now we don't know that this is going to come out the same as this other one. Like maybe what we should see here is, because this is live across the call to read, right? So maybe what we should see here is that the v.1, because that's going to get uniqueified, right? That v.1 is in conflict with RBP. I'm hoping that that's what we see. So let's run this test. Okay, so we get it hitting vector type variable there because there's a call v.1, and then the conflicts with RBP are v.1. So I think that's reasonable. Let us take these and make these assertions and this is going to be RSP. Okay. All right. I feel confident about that. I'm much more confident. So maybe what we can do is go, okay, so that's all the callee save registers. Let's check all the caller save registers. So how can we do that easily? Let's duplicate that block, and we're gonna take, let's just oops, that's not what I wanted, but we'll do this. Yeah, that's not gonna work. All right, it's fine. Okay, and I think some of those might be bare imports, but we'll just make that consistent. Let's see if that is the case. It is the case. So, okay, so I think that we're getting, our algorithm is actually correct. The assumption was wrong in that they should always be in conflict with those registers, even if those registers aren't live. And I think that that's not the case. In this program, it doesn't matter. Like, the only thing it would be in conflict with is RSP, because that's live at the end of the program. So, okay. Let's remove that echo. Well, you have to get rid of the thing too. Okay, that feels good. Yeah. All right, we got about 20 minutes left. Okay, I think that we've satisfied this requirement. And I feel pretty good about the tests. So let's source test. Let's make a okay. And then finally, allocate registers. That's all right. Well, 1 second. Let me fix whatever this warning is. Oh, things that are no longer imported. Okay. Hold on. More warnings. Where's the warning? pprint. Okay. All right. So the primary change to allocate registers is adding an auxiliary. Oops. I hate it when it does that. Adding an auxiliary function for handling definitions, with one case for function definitions. The logic is the same as described in chapter 3, except that now register allocation is performed many times, one for each. Yeah, so this is basically what we were doing before with all the other passes that have to update for do it for every function. We're doing the same thing for allocate registers. So let us go ahead and change this. So this is going to become lfun. This is going to be def call queue as x86. And then, right, so our allocate registers, let's rename this function. This is going to be, we're going to make a new one. Nope. Well, why am I doing it like that? We're just going to duplicate that. We're going to rename this allocate registers definition. And this is going to change to definition. Okay. And then down here at the bottom, we say this is definition. Okay, and body is blocks. Okay, so now it's we are just going to have input dot defs list map allocate registers definition, and then reconstruct the program. Pretty straightforward. Okay, so I don't think that there's anything else here. Right. Okay. Allocate registers. I think that let's just, since we've made this adjustment, let's find out what's broken. All right, so we need to handle the other instructions. Okay, this is very straightforward. I think that this handles we're gonna translate location already handles globals, does it not? Let's find global. It's not even referenced in here. Okay, so like that's right. It only says if it's a variable, replace the variable. So this is fine. We will just you know, do like we did up here. Easy enough. Excuse me. And then I think that covers it. All right, let's look at the tests and then we'll wrap up for the day. I have a lot to do around the house because I am leaving town tomorrow. Going for an on-site at work. Okay, let's do the same bits we did before. So these things need to be copied over. And except we need build interference. Okay. Up at the top here, this becomes elf fun. This becomes def call queue. Okay. Yeah, I hate doing this. Okay. How many functions are in here? How many tests? There's only 4. And I think that, yeah, this shouldn't be too bad. All right, let's start with our old friend conclusion, main conclusion. Let's just go ahead and replace all of those. Okay, so this is going to need to become let's go up here to one of the simpler ones. Okay, so it's going to need to become something like this. And then program just becomes main. And we can get rid of this. We don't need base program. Why does it think that's unused? Oh, because I reassigned it. Okay. So types. I don't know what this, where is this type? What was this supposed to be used before? Main types? Okay, so I think there's a thing here where we need to say, yeah. So we need to put that on the definition because before it was put on the program, right? Okay. I don't know why I have this weirdness in here. Let's just say this is start block. And yeah, I must have been trying to echo it or something at some point. Weird. Okay. Here we go again. You know, old me probably is regretting having done all of this, well, now me is regretting having done all of this manually. Old me was probably thinking, no, this isn't ever going to get out of control. Wrong. I was so wrong. Okay. Okay, so here I actually want to say, let's rename that to main2. Okay, and I think that this one's going to fail, but we'll see. This should be straightforward. So that's saying the root stack size is 1. Let's do this. Okay, root stack size is 2. Okay, and we need to import that and import that. All right, so another thing we could do or should do is look at having some of our other examples and like make a test for that. I kind of don't want to do the one that passes functions as arguments. The one with the map bit, but I think it'd be interesting to do this one. So or we could slightly modify it. Actually, slightly modifying it might be good. I don't think it's going to be like that, but let's say main.label just to make sure. No, Gleam test. I don't want to commit. Just type it, Sean. Okay, so we'll need to look at that. Let's look at unused variable. Okay, so that was actually main, so that came out in the order that I expected. Let's echo main blocks and echo inc blocks. See what happens. Okay, so main loads inc into RCX, moves 41 into RDI, tail jump. Okay, so here's a problem. We did not note that this still has a variable. That's wrong. One thing that we could do as a global kind of check in these, you know, obviously I'm not I'm not doing all of this correctly, but we could check that none of the instructions have variables as locations. So, or variables as arguments. And I think with some of the things that we already have, that would be straightforward. But let's go back in here, and I made a mistake in this tail jump, in that this needs to be translate location, label, assignments. That is a bug. That is a genuine bug. Okay, so now it actually does tail jump from RCX to 1. Okay. So 1 is the arity, right? Okay. So let's look at inc. Moves as RDI into RCX, RCX into REX. So this will get eliminated as a redundant move by patch instructions. Adds immediate to REX and then jumps to conclusion. Okay, so I think that looks reasonable. I'm curious about like what can we actually test here, and maybe we just make a snapshot. What do you think? Snapshot? Let's do a snapshot. Okay, so we will follow the pattern we did over here. Way down here, okay, it's gonna be similar to this. Because what we care about is import, import, and I think, you know, this still has the liveness information. At this point, we will have assigned everything, so I don't think that we need to emit the liveness information. So this could be we really only care about what the instructions are, right? it's body, not instructions. Okay. Okay. So let's have a look at that, and we will rename this because this is wrong. This title's wrong. Oh, for Pete's sake, come on. Okay, allocate registers, functions, test, blocks. Hi, Chris. Good to see you. How are you doing? Okay, so we have a new new snapshot. This is fine. RDI, RCX, RCX, REX, add one, REX, jump to conclusion. Okay, and then main moves inc into RCX, then 41 into RDI, which is the argument register, and then tail jumps. Good, just caught a Pokemon Go and caught Mewtwo. Congratulations. Congratulations, that's great. Okay, interestingly, we probably don't need this dict from list here, but it's fine. It'll make the order stable, so that's good. Okay, so let's run Birdie, and we're going to accept that snapshot. That's pretty good. I think we should go ahead and do the more complicated one, and just do a quick walk through it, and then we'll call it on the stream for today. So let's get our. Do we have that other example in here? No, but let's grab it from somewhere else. There it is. This thing that we've done a bunch of times. Okay, so, and we'll do this as a snapshot test as well, and then just and we'll have a look at the snapshot and see if it makes sense. The main thing that we want to do there is make sure that the contents of the instructions are all registers or stack locations. Yeah. The other thing that we probably want to look at is making sure that registers that need to be caller saved are not allocated to in the call. So that's sort of an interesting thing to have to assert. But let's run our let's just go ahead and run. Oh, it has no snapshots to review. So let's just run Gleam test. It'll write a new snapshot, and let's go have a look at it. Okay, so inc is going to be the same. No big deal there. Okay. Main, remember, is going to have multiple blocks. So that's good that LEAQ went into a register. Inc also went into a register. Okay, and then we're doing the allocation checks. Okay, and we can we'll look at main block 2 and main block 3. This is again the garbage collection branching. So we don't really need to be concerned with that other than let's make sure that they only use registers or stack locations. Okay, so main block 1 is, remember this program is create a vector containing 0 and 41 and then call map inc in it and then extract field 1. Okay, so the second field. Okay, so this is the vector tag for. Okay, so R15, what was put in R15? Oh wait, R15 is the heat pointer, right? So this is saying move the value from R11, the free pointer, into R15. Okay, and then it's moving back into R11. So that's kind of a meaningless move, potentially. Okay, so R13 was the value that, sorry, I don't know why it's not letting me highlight, is the value that was put in for field 1, or for the first field. So that's moved into R11 offset 8. I don't know why that's moved into RDX. I guess we'll see. Okay, and then we deref R15 again into R11. So R14 was 41, so that's going to R11 offset 16. Yeah, there's some unnecessary moves here. That's probably okay. These are the throwaway variables. This is void, immediate 0, void, and it's just throwing those into RDX and then they're never used again. So like those are kind of meaningless instructions, but they're just an aspect of our code generation. Okay, and then it's looking at what's in R15. New 0 moved in RCX. Okay, so RCX now contains the vector. Okay, R12 was inc. Okay, move that into RDI. Right? So that's the first argument to map. And then RSI is the second argument to map, and that's RCX, which we just got from the vector. So there's a lot of like, maybe we don't need to move this around all the time, but then we've got, you know, everything in the right place. Okay, so then we're using RBX, which we originally signed a map up here, and we're doing the indirect call with the narrative 2. Okay, and then we move RAX into R15 offset 0. That's interesting. Okay, and then we move R15 0 into R11. Like, this will be eliminated as an unnecessary move, right? Because you move into this thing and then move from that thing into this other thing. Patch instructions will handle that. Okay, and then it's dereffing R11 offset 16, so that's the second field, into REX. Okay, so if you're following along here, I think we did this, at least the main, correctly. We're gonna have to look at map real quick, and then you'll see here that like this is just another void move. Here we're putting the heat pointer into RDI, and we need 24 bytes, and we're putting that into RSI as second argument, and then we're calling collect. So try to collect 24 bytes if we're out of room. And then we jump into the conclusion of that branch. Okay, map. This is going to be fun. All right, so copying the argument register out, copying the other argument register out. Notice that this is, oh, that's interesting, -88, kind of bad. I'm wondering why that was given that. We we probably need to see what the expected stack pointers are. The expected stack variables. So let's not accept this snapshot. I think I want to have so we want to get the blocks, but I think I also want to capture, this is going to make us do it again, stack vars and root stack size, because that's going to be interesting. Wrong one. Down here. Okay. This negative 88 concerns me. I think that's a bug. But let's move forward. Let's see what happens. Okay, so also this would be eliminated anyway. We see it again down here. But here, like, we're moving it out of the argument register into this stack location. It's not a stack location. It would be RSP if it's a stack location. This is a heap location. It's very strange. And then R11. So these would get eliminated by patch instructions, but I would rather not emit something like that if it's just going to be wrong. Okay. So, okay. Right, so we've got dereferencing R11 into RCX. So that's the first field. And then we move that into an argument register, and then we call the past function, RBX. And then we copy that out into R12. Okay, and then we're doing the same business again. And then offset the second field into RCX, move it into RDI. Again, this would be another thing where it'll be eliminated because it's a redundant move. Not a redundant move, but like a move to one thing and then a move to another thing from the same thing. Okay, and then again we're using RBX, which is the function to be called. Okay, and then we move that out, and the function is no longer called, so we reuse that register. All right, then we're doing the allocation. So we've got answer 1 in R12, answer 2 in RBX. So after all of this business, we should expect to see R12 moved into field 1, RBX moved into field 2, and then we move that into RX. Honestly, though, this deref makes me think it should be returning, it should move R15 to RAX, but I have to think about that. Okay, and then there's the typical bits of allocation. I think that's okay. Let's run it again, so we get a new snapshot, because I want to see what it creates. So the root stack size here is 2. I think that makes sense for map, but there's 0 stack vars. So I'm wondering what that dref -88 is. What is that? What the hell? We're gonna have to find where that's generated. Okay, and the root stack size on main, I expect it to be 1, yes. And no stack vars, that's fine. And then for inc, we have 0 and 0 because we have no vectors and we have no need for the stack, for allocation onto the stack. We don't spill them. Okay, so this is fine. I think it's good to stop here. Let's Gleam run mbirdie. Okay, and this is the thing we just looked at. Yep. Okay, and so that just looks like a formatting change. Yeah, that's just a formatting change. Oh, well, I actually messed that up. So I need to revert what I did in that other test. All right, I just wrapped it in a tuple unnecessarily. Reject. Okay, so there's nothing to review there. So let's look really quickly at this and see what's different. This is just, it chose RCX instead of RBX, and that's interesting to me that changed. But that doesn't mess with the semantics at all. So it probably has to do with the fact that we moved that. Let's see, where the branching test. So if we just change this to RBX, then it's fine. I don't see that there's any particular problem with that. Now maybe some of the other assertions fail after we fix that. So it's gonna change the assignments in the other blocks. It's just it chose them in a different order, I think, is what happened. Did I change the wrong one? No, this is just... Probably the other one's going to fail because this is... No, I messed that up. Okay, so we have move RAX into RCX. Okay. And then we have compare RBX with RCX, right? Because we renamed that. So in the block above, I forgot that this is like... Okay, and then we still have a problem there. What happened? RAX, RCX, RBX, 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 and RDX. So RCX. All right, finally the a else expected. This is moves into rdx. Call readint, move rex into rdx. It's actually, it switched it to rcx. Yeah, like this, it doesn't actually matter that much, but it just chose a different ordering for them. Add Q, move Q from RCX into RX. Okay. All right. So now let's look at this multiple roots test and fix that and see what's going on. Okay, so we make A. Right, so this is making sure that both the inner vector and the one that wraps it are live at the same time. So it should be, the root stack size should be 2. Why is it saying 3? Why does it say 3? I guess I can just do pprint.debug. That prints to the console. Main.blocks. Let's look at that. Okay. Ooh, and it comes out ANSI printed. Yay! Okay. Why do we need to allocate so much? It should only have, oh. Okay, there should be 3 roots. Note that we do vector A here. This is wrong. The root stack size should be 3. I don't know why my original assumption said it should be 2 and why that ever worked. Because look, we've got this, we've got that. That's a separate allocation from this one. Yeah. I was like, why are there so many dang blocks in this? You know, some of it too is we're showing off the liveness sets, but like we don't need to keep those in there for just this pretty print, but they're part of the block. So and we don't clear them out after we have allocated registers, which we could, but we just don't. So yeah. Yeah, there's a lot of jumping for all those allocating vectors. Lots of blocks there. I think I think the reason why dref R15 zeros there is like when we call allocate, R15 must be the stack. Here's that negative 88 again. I'm really curious, other than in there that snapshot. No. So here, okay, so R15 is the pointer to the root stacks. I don't know why it needs to, oh, negative 8 times A. If A would have to be 11 for that to be negative 8. Yeah, I think maybe the task for next time should be, let's look into why we're getting past 11 into that root stack assignment. Like it's right here. Assignment is just an integer. The problem might be that it's getting assigned 11. Oh, and we subtract 11 here. So that's actually what we need to do, is that 11 being the first spot. Yeah, there's a bug here with this. So we need minus 11. Simple bug. And this is going to break the snapshots. But that doesn't look, why is that backwards? That makes more sense, right? The root stack slot 0 makes way more sense than negative 88. Okay, where's that preprint that we did? Yeah, let's get rid of that. Okay, so we yeah, it's not even in that file. I don't know why the diff is showing removed that, added that, when it's actually backwards. And then down here it's like removed that, added that. Okay. I'm just going to accept, and then negative 88 is not in there. Okay. And this one, negative 88, is not in there. Well, this one it wouldn't be, but yeah. Okay. Let's make a commit. make sure I resolve all the warnings here. Like, we're not using, are we using pprint? Oh yeah, we are for the snapshots. Okay, that's fine. Why don't I use this since I have it? Okay. All right. 7.9 point what? 3. Allocate registers. Update allocate registers. I'm going to say also fixed bug with incorrect root stack offset. First slot became -88. All right, and let's go. Oh shoot! What did I? Why is that? Let's just stage all of them. I'm gonna have to figure out why my editor is not auto formatting for me. All right, that's the stream for today. Thanks for hanging out extra long. I was pleased in general that we didn't have to make too many changes to these algorithms, and that certain aspects of it we were able to verify are reasonable, based on having the ability to make those snapshots for our tests. So good stuff. Thanks a lot. See you next